The next example, the seawater flow steady through a simple conical shaped nozzle at the end of the fire hose. If the nozzle exceeds velocity must and you must be at least the 20 meter per second. Determine the minimum pumping capacity required in the cubic meter per second. Okay, we can draw the control volume like this. Okay, this is the control volume. Okay, and we put the first point is the inflow and second point is outflow for the nozzle. And for the first point, theta is 180, and this point outflow is 0. So we can start from the Reynolds transport theorem for the continuity equation. So this term is because of the mass in the system doesn't change with time, and the second term is 0. The mass doesn't change inside the control volume, so just only the mass flux into the boundary. Okay, so we can write that for the inflow is equal to rho v1 dot n is equal to v1 a1, and so we got the negative sign. And for the outflow is rho 2 v2 a2. Okay, so in this case it means rho 1 v1 a1 is equal to rho 2 v2 a2, and we use the same fluid, so rho is equal, so we can prove that v1 q1 is v1 a1 is q1 is equal to 20 meter per second times the area. So q1 is equal to 0.025 cubic meter per second. The next example, the tanks is being filled with the water by two-dimensional inlet. Okay, air is trapped at the top of the tanks. Water height h. For expression of the change of water height dh over dt. If is a d1 1 inch, d2 3 inch, v1 v2 and a tanks. Assume that temperature of water is 20 degrees Celsius. Okay, that this is a given data. d1 d2 v1 v2 a tanks. You want to derive the equation for dh over d2 and find the numerical solution, numerical value for. So we start from that actually this tank is the three-dimensional tanks. So that is the 380 area of the tanks, and we can apply the Reynolds transport theorem from this and apply the control volume based on the dashed line along for these tanks. And you can see that inflow at the point 1, that is the point 1, that is the unit vector normal to the area, and v1 and unit vector and v2. So theta for inflow is 180 and outflow is 0. So we can substitute in the equation for the control or the self-control surface. So we got this is for v1 is for at point 1 is v1 cos 180 and v2 with cos 0. Okay, for next, you can move the chain of control volume to the left hand side. equal to in this case it convert to low 2 V2 and A2. And low 2, low 1 Q1. Okay. And for the second term, the change of mass inside the control volume, we can write in terms of the rho dA is mean rho of water times area of the tanks times the H. Okay. And plus the rho of the air times the area of the tanks and the length of the top of the water. Okay. But for in this case, we assume that the mass of air is constant. Okay, so this term is equal to 0. The mass of air is constant. Okay, so we can come up with a solution that rho MAT is over dt equal to rho 1 A1 V1 plus rho 2 A2 V2. This along with the direction of the flow. V2 is this direction. Sorry, I'm missing. So V2 is the inflow. Okay. So it means at that point the V1 is the theta at 180 and V2 is 180 as well. Okay, so it means we got an all negative. Okay, we move to another side, so we got all positive on the. Okay, so we can find that dH dt is equal to A1 V1 plus A2 V2 divided by AT area of the tank, because in this case rho 1 rho 2 equal to chlor water. So it means dH dt is equal to Q1 plus Q2 divided by area of the tank. And next step, we can find what is the Q1 is equal to A1. 1 is equal to pi over 4 convert full square foot 1 over 12 foot is equal to 0.016 cubic foot per second, and for Q2 is equal to A2 V2 convert to foot time velocity. Okay, next we substitute in the equation of dH over dt. So we got 0.016 plus 0.098 and divided by 2. So that is the change of water with time is increasing 0.57 feet per second.